Okay, so welcome to today's lecture. As you have probably seen, I've given up trying to translate the rest of the slides for this semester, so we'll be using the German ones. But that should not be a problem because I think most of the special vocabulary are actually quite straightforward. We stopped last week with the discussion of the Newton Cotes formula for numerical integration. You will remember that actually numerical integration looks something like this. You have a function, you want to approximate the integral under the function, and just like the Riemann integral, you are using some geometrical shapes to approximate this space under the function. And the Newton Cotes formula is given by this. You take the integral and you approximate it by taking a sum of weighted function values, which makes sense because here you need the sides of these rectangle shapes. And actually, you know that this here, this is the function value of, say, let this be x0, and this of course is also equal to fx0. So if you take the function value, you know how long this side of the trapezoid or the rectangle is. Yeah. So you take function values, for example fx0, and you have to weight it times w1. Then you take, for example, this function value fx1 times w0 or omega 0, and so on. And you see that in the end you get the sum of the weighted function values. And actually in this case the function values are weighted with these weights 1 over b minus a and the integral over ij. What is ij? Ij, as you might remember, those are the Lagrange basis polynomials, which are known. The values of those integrals can be easily retrieved from ancient books or from a computer or even from a calculator. And this is a Newton Cotes formula of order n, if you use n plus 1 knots. For n equal to 1, you get the trapezoid rule with 2 knots, 2 Stützstellen. For n equal to 2, you get the so-called Simpson rule. And in this case, you're using a rectangle or a trapezoid. And actually, the idea is that the geometrical shapes get a little bit more complex, have more sides, and in the end, of course, your integral is approximated in a better way. So by increasing the number of knots, you are able to increase the accuracy of your approximation. And you can see here that, of course, in this very crude approximation, you still have some error left, because actually here, this is of course where your integral is not quite accurate, but by increasing the number of nodes or knots, you might achieve a better approximation. And this is the idea behind numerical integration. Now, in the Newton Cotes formulas, the nodes are explicitly given, and afterwards you simply select the weights that will give you a good approximation. In the alternative, the Gaussian quadrature, you are doing it in a slightly different manner. You're choosing both the nodes and the weights in such an optimal fashion that the approximation is better and is optimal in a certain sense. So we are trying to approximate the following integral from a to b over w. Now I think it's omega times f dx by a quadrature formula that is given by a sum I starting with 1 up to n over those weighted function values. Why are we not trying to approximate the integral of the function f, but actually of omega f? A very simple idea. In some cases, it might be that you have a function that is actually quite difficult to approximate and to calculate the integral. And then you can try to isolate certain singularities in a weighting function and simply to put it into into omega of x, and then for certain weighting functions omega, you just know how the integrals look. So this is just one little trick you can try and you can apply to more or less to isolate some problems and to push it into another function and to solve it in a more ideal way. Of course, just a regular integral of x, for this you simply set omega to 1. You have a weighting function omega that is equal to 1, and you just get your regular integral from high school. Okay, so how should we choose those nodes and the weights? The nodes should be the zeros of an orthogonal polynomial of order n. You can prove this, you can show this in Gaussian quadrature, that you should choose the nodes and you should set them equal to the zeros of certain orthogonal polynomials. And what are orthogonal polynomials? As always, if two things are orthogonal, it means they form, how do you call it in English? In German we would say sind im rechten Winkel zueinander. No? Sind halt orthogonal zueinander. So here, in order to apply this idea of orthogonality to polynomials, we need a scalar product. You might remember this from high school. Two vectors are orthogonal if their scalar product is this and that. And here we're using this scalar product. Delta ij of P1 and Pi and Pj is given by the integral over Pi and Pj, maybe with a weighting function, omega. And when are two vectors orthogonal to each other? When scalar product is 0. Yeah. So if this integral is 0, you know that Pi and Pj are orthogonal. Okay. And then the weights are simply given by the integral from a to b over omega. Let's assume for the moment that omega is just 1, it's a constant function, and then we have a product x minus xj over xi minus xj, which is known. These weights are known. You can simply insert the number of nodes you're using. So if you're using 10 nodes, simply set n to 10, and then you see x minus xj and so on. You need the nodes, but those nodes are the zeros of these polynomials. A little bit more specific. In numerical analysis, actually, there is a whole branch of research and teaching that is just devoted to orthogonal polynomials. You can fill whole seminars on orthogonal polynomials. One example, for example, are the so-called Legendre polynomials. If you take the zeros, the roots, Nullstellen, of these polynomials, and you set omega to 1, you get what is called Gauss-Legendre quadrature. If you take a different weighting function, the exponential function of minus x squared, so you have a function and you can see that you can isolate the exponential function of minus x squared You simply put it into the weighting function, and then you can approximate the integral of the remainder of this function. And in this case, you get the Hermite and Gaussian Hermite quadrature. How do these roots and zeros look? We don't need to know this. You simply, if you use a computer and if you take a function that tries to approximate the integral, you will simply see certain options, and you can choose Gauss-Hermite, you can choose Gauss-Legendre, and here in this case you just see that as note, you're not simply selecting 1, 2, 3, 4, 5, 6, but you are using more sophisticated nodes. You're simply selecting the roots of these orthogonal polynomials, and then afterwards you can see that the approximation is much better. Okay, so for these orthogonal Hermite polynomials, for example, these are given by the following recursion. H minus 1 is 0. H0 is 1 over pi taken to the fourth square root of pi. And hj plus 1 is given by x times hj minus a root times hj minus 1. Does everyone understand how such a recursion works? It works like this. You are not defining these polynomials in an explicit way, but you're simply giving the rule with which you can construct the next set of polynomials. So for example, you start with h minus 1 is equal to 0, and h0 is equal to 1 over the fourth root of pi. Now, the next would be h1. h1 is x times times x0. So you take the line before, insert it into the last line, minus the root of times hj minus 1, which would be 0. Then you have h1. Then to construct h2, you would have to resort to h1 and h0. For h3, you need h2 and h1, and so on. And you need, in order, for example, to construct h8, you need h7 and h6. For h7, you need h6 and h5, and so you have to go back and back and back, and this is why it's called a recursion. You have to resort to the polynomials you've constructed in the previous step, and this is how you can construct the next one, and then the next one, and then the next one. So this is a recursion. Ist das klar? Ich kann es auch nochmal auf Deutsch erklären. Ja, Sie haben es nicht explizit gegeben, Sie müssen es einfach rekursiv machen. Ja, um H35 zu rechnen, auszurechnen müssen Sie H34 und H33 nehmen. Und dann müssen Sie immer einen Schritt zurückgehen. Deswegen fangen Sie bei H0 und H-1 an. Die sind explizit gegeben. Und H3 plus 1 ist Ihre Rekursionsvorschrift. Und dann können Sie es dann so langsam rekursiv aufbauen. So. Here you know these polynomials, and then you can estimate the zeros. Die Nullstellen. Again, you don't need to do this by hand. You can simply look it up in a book or in the computer. The weights are then given. For example, for the integral from minus to plus infinity, wi is 2 over hn, first derivative, squared. And here you can see the derivative of hj is square root of 2 times j times hj minus 1. Again, this is something interesting here, and this is not surprising. These special polynomials and these special basis polynomials, they usually possess special properties. Like in this case, you can see that you can easily calculate the first derivative of any polynomial by simply resorting to the previous one times the square root of 2 times j. And this these are the weights, and then of course you need the zeros of those Hermite meet polynomials to calculate the nodes. So let's do this here. First of all, in MATLAB we try to construct those polynomials. H poly 1, H poly 2, you can see these are just the first two polynomials. And for j equal to 1 until n minus 1, H poly 3 is the recursion you've seen on the previous slide. And then, because we are moving one step ahead, we need to reset the two previous polynomials. This is why we set H poly 1 equal to H poly 2 and H poly 2 equal to H poly 3. This is just the recursion you've seen on the previous slide. And then what we do next is we sort the roots of H poly 3. So, what are we doing? For example, let's assume we want to calculate the integral using 20 nodes. 20 Stück. Then we need the roots, the zeros, of a Hermite polynomial of order 20. So we need H poly 20. So we run the recursion 20 times, and then we take roots of H poly 3, which means that we take the last polynomial, which is of order 20, and roots will give you the roots in MATLAB. We sort them because we don't want to have 1, 5, 3, 8, 7, 1 again, but we want them sorted, right? The nodes should be sorted 1, 2, 3, or 1.1, 2.7, and so on. So we have the zeros of the Hermite polynomial. Then W is just a vector of zeros, and we'll fill this vector with the weights. Here for I equal to 1 to n, Wi is equal to 1 over n over the value of this polynomial, poly 1 squared, at the roots. And here we are calculating those weights. Those are the weights, and these are the nodes. And then the quadrature is obviously just the sum of the weights times f at x. And this is what we do next. Here we take Gauss-Hermite and a and b. Those four values here, those are the nodes, and those values here, those are the weights. And to calculate an integral, to approximate an integral, we now need to take those nodes, insert them into the function, calculate the function values, and then use the weights, and we'll get the approximation for the integral. So let's do this. GH quads, n and f. We select the number of nodes, assuming, and this is quite clear, the higher the number of the nodes, the better the approximation will be, and we want to approximate this function f. So xw, Gauss-Hermite, f nodes, those are the function values, and the integral is just w times f nodes. If we now do this, and we start with 2 nodes, you can see the answer will be, and we are trying to approximate this function, so it's 5 times the exponential function of x. This is f of x. You can see that if we are using 2 nodes, the answer will be 11.1717. If we are using 10 nodes, the answer will be 11.3794. And if we use 100 nodes, the answer will be 11.3802. You can try to measure the accuracy here, but what you can obviously see is that it's quite striking that even with just 2 nodes, there is not too much variance and not too much variation in the answer going from 2 to 100 nodes. And this shows you how good this approximation probably is. that even if you use 100 nodes, the first guess with just 2 nodes is already a very good approximation. And this is one of the this is a simple observation that a quadrature formula like Gauss-Legendre or Gauss-Hermite is much better than a Newton-Cotes formula, where you simply set the nodes to be 1, 2, 3, 4, 5, 6. So with equidistant nodes, you will get a much worse approximation than this here with Gaussian integration, because you are selecting both nodes and weights in an optimal fashion. Okay. Now, MATLAB can do this as well. You don't need to program this by yourself, but you will see here that, for example, there's a function quad for quadrature that does it for you. But in fact, here we can see that there are two types, quad and quad L. Quad L uses an adaptive Lobato quadrature. You don't need to remember this. It's just an alternative. And it's quite clear that the functions that are used here are tuned and optimized, even in comparison to the Gauss-Hermite or Gauss-Legendre quadrature. Let's look at this exponential function of minus x times sinus of 10x from 0 to 2 pi. And if we do this, it's one line in MATLAB, and you can calculate the integral just by using quad f 0 2 times pi, and you can see that it will give you the answer quite quickly. Okay, so this is very simple deterministic quadrature in MATLAB. Again, remember, when it comes to calculus and differential calculus, not really, but when it comes to derivatives and integrals, it's a challenge to approximate an integral. It's not a big deal to approximate a first derivative. Why? The first derivative is already defined as a linear approximation to a function. So you simply take a line, you plot it, and you take a straight line to a function, and you get the first derivative. So usually you will not even find too much documentation on an approximation of the first derivative. It's quite different for an integral. And in many cases, you will see those functions in between working in for example, statistical estimations. Now we can also do Monte-Carlo integration. This is quite interesting, actually. We are now assuming we want to approximate this integral of a function g from 0 to 1. We can actually interpret this integral not just as an integral, but as an expected value. You can see and you can view this as the expected value of the function g with a uniform random variable inserted into g. So this is equivalent. This is equal to the expected value of g, and if you insert a uniform random variable in it. But if this is a mean of a random variable, this also means that we can simply try to approximate the integral by using Monte-Carlo simulation, by simulating from an appropriate random variable and using the sample. This is meant with STP, Stichprobe. You can use a random sample and approximate this integral. So what do? We simulate m values from a uniform distribution on the open interval from 0 to 1. Gleichverteilung in German is a uniform distribution. Be careful with those German words. We can distinguish a uniform from a identical distribution. In German, they look the same. Gleichverteilung und identische Verteilung. It sounds the same, but these are two different concepts. A uniform, eine Gleichverteilung, uniform distribution, is a distribution that sets the same probability to each event. So a dice has a uniform. If it's a fair dice, it has a uniform distribution on 1, 2, 3, 4, 5, 6. An identical distribution simply means that two random variables have the same distribution. So it might be a Gaussian and a Gaussian distribution. A Stevens-T and a Stevens-T. This is what we call identical distribution in English. And in German, the two words are quite similar. Gleich und identisch. Gleichverteilte. One could assume that if you have two gleichverteilte Zufallsvariablen, it means the same as identical distribution. But this here is a uniform distribution. By the way, how does it look if you have a continuous uniform distribution? The distribution function looks like a? No, it's a rectangle. Yeah. It's a rectangle, and obviously this here has 1 probability. Yeah. In the discrete case, you have this here. You have lines and little dots here. This is a case of a dice. 1, 2, 3, 4, 5, 6. Das ist auch der Grund, warum man es im Deutschen Rechtecksverteilung nennt, im stetigen Fall. Okay. Now, the integral is approximated by 1 over m times the sum over all those function values when you insert those uniform random samples into the function g. Now, the law of large numbers states that it should hold for m converging to infinity. So for an increasing number of samples, this approximation should be, the limit of this approximation should be the integral we are looking for, because it's the expected value. So what shall we do? We simply take a uniform random variable, and we simulate from this uniform random variable. We insert those simulated values in the function g. We sum those values up. We divide them by n. We take the average, and we get our integral. Remember, this sounds like a very special case, but it's not. Remember that actually it is no problem to convert any integral ab of, say, h to an integral of 0 and 1 of h of t of x with a transformation of the variable x. You should simply switch the variables and transform x such that this integral from a to b is equal to the integral from 0 to 1 or from -1 to 1 for a different fraction. Again in German. Sie müssen sich nicht an den Integrationsgrenzen stören. Sie können jedes Integral durch einen simplen Variablentausch von a nach b auf ein Integral von 0 bis 1 überführen. Deswegen nur die Tatsache, dass hier das Integral von 0 bis 1 über g von x gegeben ist, heißt noch lange nicht, dass Sie immer nur dieses Integral ausrechnen können. Sie können jedes beliebige Integral, jedes bestimmte Integral, können Sie so ausrechnen, indem Sie einfach die Variablen im Variablentausch durchführen. Ist ein bisschen tricky, aber es ist jetzt auch keine große Mathematik. Yeah, and then we can do this here. We are trying to approximate this integral just of the exponential function. You know this, you can calculate it. Analytically, it's exponential function -1, and it's approximately, if you use your own calculator, it's 1.7183. And we now use the function in MATLAB rand m comma n, and it generates an m times n matrix of random samples from a uniform distribution on on the open interval from 0 to 1. Has anyone a calculator with him? No. Just want to check this. Yeah. I can see it right now. Yeah. 0 point, you have R&D and rand pound, and even your calculator can generate those random numbers. You have to look up your documentation of your calculator, but you could do this not just in MATLAB, you can do this on your calculator. Yeah? This is even 20 years ago, my math teachers in high school did this without this. Let's play lotto, let's play bingo or whatever, and let's generate some random numbers with our calculators. Yeah? Of course, this is much quicker, and it would take a lot of time to generate 1 million random numbers with your calculator. But here you can see it's not the exact solution, because obviously the exponential function is not known analytically. Well, it's known analytically, but not in this case here. But we are looking for a solution that is close to 1.71. And here you can see that if we take 10 random numbers, the first result will be 1.83. Close, but not very good. We repeat this, and suddenly the result will be 2.03. Not very close. And you can still see you have a large estimation bias and large variance in your estimation. Now, if we take 1 million random numbers, we are getting quite close. 1.7189. Next try, 1.7178. So even with 1 million random numbers, you can still see the estimates varying around the solution. And it's still not converging. Meaning, yes, you can do this. Yes, it will give you a good result if you are able to increase the number of random samples just high enough. But even with 1 million samples, it's still not empirically converging to the solution. Now, should we do this? Well, in this case, no. This is complete overkill. Random Monte-Carlo simulation and Monte-Carlo integration is completely bogus in one dimension. So for this simple example of the exponential function, you will never use Monte-Carlo integration. Why? You need 10 million samples, and you will need such a high computational workload just to get an estimate. You can actually achieve with Gaussian quadrature with 5 nodes. So why should you do this? Well, it's a good thing to do this in multi-dimensions. You might remember this from high school or from your statistics classes here. In many cases, you will get 2-dimensional or even multivariate integrals. So you have functions not just of x, but x1, x2, x3, and so on. And if you need to calculate integrals over more than one variable, then you will probably resort to Monte-Carlo integration. Because you no longer have those methods I've shown you, Gauss-Legendre, the Gauss-Emmy, etc., and Newton codes. You no longer have these methods at your disposal. They will no longer work. And the problem of finding multivariate integrals is so complex that in some cases you will simply resort to this brute force approach. This is brute force. There's a very simple theory behind it at this point. I mean, if you go to research, you will find better methods. But at least the idea here is very simple. The integral is equal to an expected value, so we can just simulate random numbers until eternity and let our brute force computer solve the problem by just working numbers. And this is an alternative in high dimensions. Then you can simply say, okay, let the computer do it. Because you have no better solution and no better method at your disposal. Okay. So this is what you can do here. Remember that in your average integral, you're trying to calculate a space. For example, a rectangular space under a function. Now, in multi-dimensions, you can generalize this idea. It's no longer a space below a function, but now it's volume. So you need the volume of this space A, and the integral, the quadrature, looks pretty much the same. You simply take this function. You have to simulate. You insert it, and it's just not 1 over m, but now it's the volume of this space A divided by m. This is just the generalization to n dimensions. Okay, so usually you will just use the unit hyperspace, all those intervals 0 to 1 times 0 to 1 and so on. And in this case, the volume will be 1. So again, you will have 1 over m. But this is a special case if you have this unit hyperspace. And unit hypercube. Okay. Yeah. Okay. So in some cases, you need this. And actually, you need this in option pricing. You have more than one variable, and you need multi-dimensional integrals. Okay. Any questions concerning quadrature and numerical integration? It's not that complicated. Actually, if you need it, you will simply resort to quad L in MATLAB, but you need to know how this works. You are using a number of nodes, and you're trying to approximate the integral by increasing the number of nodes, and in some cases, it's actually sufficient to just use 10, 15 nodes. Okay. Now, later on, we want to talk about option pricing. So at this point, I need to make sure that you all know the basics of options and futures and forwards. First question now is, has anyone of you taken the derivatives of financial risk management class? Okay. But you know what a financial derivative is? Everyone? Okay. Everyone knows what a forward, what a future, what an option is? Okay. Then I would say I will simply go through these slides a little bit quicker, because I know most of these should be well known. Let's start with options. You can look it up here in the investment and risk management book. An option is just the right but not the obligation to buy or sell an item. Usually we'll use a stock as the underlying, and you can distinguish American options, European options, Bermudan options. European options can only be exercised at the end and maturity. American options can be exercised at any point in time until maturity, and Bermudan options can only be exercised at reoccurring points in time, for example, on the first of each month. So it's right between an American and a European option. A long call. I've stressed this yesterday in the risk management class. One needs to keep in mind that financial derivatives are always zero-sum games. If I win €1, someone else loses €1. And second, derivatives are always in zero net supply. So I cannot produce an option like I can produce a stock. For example, I can issue stocks. Meaning that if you are the financial market and you are traders on the market, I'm a company, I will be issuing stocks, and I will try to sell those stocks to you. But if we net our positions in the whole market, we'll see that there is a positive supply surplus of, say, 10 stocks. If I produce 10 stocks, if I issue 10 stocks, the net supply will be plus 10. It's different in derivatives markets. In derivatives markets, there is always zero, they are always zero in supply. What does it mean? If I want to buy an option, I need to find someone who sells me an option. So I buy one, you sell me one, I'm long, you're short, exactly one option. If we net our positions, zero net supply, plus or minus zero. So, if we have a long call, there should be someone with the short position, exactly in the opposite direction. A long call, we buy a call option, that is, we buy the right to buy the underlying, and in the end, we will exercise the option if the stock price at maturity is larger than the exercise price, the strike price. Otherwise, we'll let the option expire and we'll get zero. So the payout and the payoff profile of this option at maturity is the maximum of ST minus X and zero. And this is tricky. Always keep in mind, this is simple, but this is only the payoff profile at maturity. So in the end, after we have bought the option, and we can still decide exercise or no exercise, then of course we know what the option is worth. The tricky part is knowing what the option price should look like today at today's time, not at maturity. And then you can see the famous hockey stick diagram. We will see that here, this is the payoff profile. So if this underlying price goes up, we'll get a higher payoff, and we need to pay a certain premium, the price for the option, C0. So if we let it expire, we'll lose money, and at some point we'll break even. And if the payoff of the option is higher than the initial price, we'll make a profit. GT stands for to quite clear. Short call, the opposite. Hockey stick goes down. If you would net those two, you will see that the net profit and loss is always zero. It's a zero-sum game. If I lose €1, you will win €1 and gain €1. Long put, we buy the right to sell the underlying. So we can sell it at the strike price, and we'll make a profit if we can sell it higher than the current market price. So the maximum of X minus ST, or zero, is our payoff. This is what the hockey stick diagram looks like. We'll make a profit if just the market price goes down, because we can sell it at X on the market, and we can replenish our supply and our need to sell it on the market at the spot price. And the spot price here, for example, would be zero, and then this would be our payoff. We need to pay the price for the option, and this will reduce our payoff, and then this would be our maximum profit, or we'll make such a loss. One can see that in some cases the loss potential of an option contract is unlimited. Yeah? Hypothetically. Short put, for example. Here you can see that if the price goes down, this will be our payoff, and this will be our maximum loss. And in some cases, we'll make a profit that is bounded upwards by GT. Those are options. Plain vanilla options. In the financial risk management class in the bachelor's degree, I also discuss more exotic ones, binary options, barrier options, Asian options, and so on. The only difference is that these options have a slightly different payoff profile. Yeah? Okay. Forwards. What is a forward? A forward is an unconditional derivative contract. You buy something in advance, or you sell something in advance, and you agree that, for example, let's assume forward is an OTC contract. We two agree that I want to buy 1 ton of steel from you in 1 year, and we fix the price today. So we say 100 euros for 1 ton of steel today. You can distinguish two things: physical settlement, cash settlement. First of all, physical settlement would mean that we have to agree where we want to exchange the money. and the steel. Let's assume it's oil, then usually oil will be exchanged at Rotterdam and the chloride in some storage unit. Do we want it? Usually not. We are only interested in the hedging effect. So we'll do the second option, cash settlement. For example, in the end, if we observe that we've agreed to a price of 100, but oil now costs 150, I am buying for 100. It costs 150, and instead of physical settlement, we'll just agree that you will have to pay me the difference of 50 euros. This is cash settlement. No physical delivery, but you're simply settling the contract with cash. Then, what are you agreeing on? You can see the slides have undergone some rudimentary translations. Simply, I searched and replaced some words. If you are long in the forward, you are buying the underlying in advance, and you are fixing the price today, and then you can distinguish two prices. The forward price you agree on in the forward contract, and the spot price you can observe on the market. Spot price in German is Spotpreis oder Kassakurs. Forward Kurs, der Terminpreis oder der Terminkurs. Okay. In some cases, using the forward contract, it might happen that, for example, if the price for oil goes up 200, 500, 1,000, you realize that you are piling up losses. And in the end, you might simply go, oh, sorry, I don't have any money. I cannot settle this contract. And in this case, I could see this coming. I can see that you are losing, you are bleeding money. So to prevent you from defaulting on this contract, I might ask you in between, please pay something in advance, because right at this moment, you've already lost 500 euros on this contract. This is called a margin payment. And in forward contracts, you might agree, you might have a clause in the contract that says that one party has to pay the other party a margin payment if the losses are higher than a certain threshold. This is a margin payment. This will be more important with futures. Okay. So what is your profit or your loss? Quite simply. At maturity, the difference between the agreed upon forward price and the spot price. KS or KT minus FS. This is the profit. If the spot price goes up and I've bought at FS, I'm earning 50 euros. Other way around. Again, a zero-sum game. You lose 50, I win 50. Okay. Now, you are short and I'm long. I've bought the forward contract, I'm buying, so I am long, you are short. And in contrast to options, this is a very linear product. With every euro, the spot price increases, the value of this contract will also increase by 1 euro. And the other way around if you are short. What is a future? A future is an exchange-traded version of a forward. The forward contract works OTC. So, for example, if you are E.ON and I'm an energy trading company, we might want to trade on a forward contract OTC. So we'll simply agree to a contract we can set up ourselves. We could, for example, work on a forward contract for 1,000 products of GTA 6, Red Dead Redemption 2, whatever. We can choose the underlying just as we want, and we can fix all the details of the contract individually. This is a forward contract. It can be traded. By the way, it can of course be settled if both parties agree to. For example, if we have a maturity of 1 year, and after 6 months, you say, I want out, and I say, yes, I want out too, we will simply look at the difference between the forward price and the current spot price, and can settle it, if both parties agree to it. But this is a given, of course. If you want out, and I say, well, no, the prices are going up, I can keep my contract. I can ask you for a margin payment, but you cannot. Go on. Future is the exchange-traded version of forward, it's the same. The difference is that you are not agreeing to a forward price, but you can observe the futures price on the exchange. Those exchanges are different than stock exchanges. They're usually separated, and they're called futures exchanges. And because most of those underlyings are commodities, those are usually commodity exchanges. Chicago Mercantile Exchange, the CME, Eurex, at Frankfurt. Another big example of a commodity exchange. If we had it from the window here, we would see the European Energy Exchange, one of the growing markets of electricity. I had this discussion yesterday with the bachelor students. They wanted to know whether how this works. I have to admit, I don't really know. Because I just know the electricity market is quite peculiar. You cannot store electricity, or it's very difficult to store electricity. You can pump it up into lakes and then let the water flow down. Later on, you can try to liquefy. You can try to use electricity and artificially, I think you can artificially produce gas. You can try to produce hydrogen. This is one of the futuristic ideas how cars will run in the future, that you're using night electricity in those gas stations, and you produce the hydrogen overnight that will be tanked into hydrogen cars over the day. This might be an idea, but you cannot really store electricity. And the electricity market is quite peculiar. For example, you sometimes have negative prices for electricity. You know why?
In case you produce too much electricity and nobody takes it.
Yeah. If you produce too much electricity, the costs of shutting down a power plant are much higher than simply, and sometimes you cannot do it technically, but even if you produce too much energy, the costs of shutting down, for example, gas and coal plants, is so high that actually you are rather willing to pay a negative price. You are paying in order to supply electricity in the night, and it's sold off to other countries, maybe. Yeah? So this is why the energy market works quite differently from a commodities exchange. Let's say gas or oil, for example. Okay. Now, again, some notation. The difference here, again, is the forward price is not agreed upon, but the futures price is observable on the futures exchange. Then we have what we call a basis. A basis is just the difference between the current spot and the futures price. By the way, the paper I sent you around today for the next seminar that uses an exogenous shock to basis risk in the natural gas industry. This is the basis, the difference between the spot and the future price. And basis risk is, of course, the risk that this basis will widen or sharpen and close. And this here is the basis. And we'll see how this works out later on. Quite clearly, if we are looking at a future that is close to expiration, the futures price, the value of this future should equal the spot price. Because if you take a future that runs only 5 seconds, so you can now buy something with delivery in 5 seconds, this is the spot price. This is called the conversion of the futures price to the spot price. So with the maturity of the future contract closing into zero, the future price will converge to the spot price. Now, another difference between a forward and a future contract. As you can observe the future price every day, you can calculate the daily losses or profits from this future contract. You simply know that you have now earned 5 euros on this contract since yesterday. And as you can observe these daily changes in the prices, in the futures price, you can mark your contract to the current market price. And in the end, it's quite simple. if you have a future contract that runs 2 days, I make a profit of 5 euros today and 5 euros tomorrow. If the future prices change, 5 euros yesterday and 5 euros today, tomorrow, my profit from this future contract will be the sum of all those daily profits and losses. Meaning, instead of simply piling up profits and losses, like in the forward contract, and afterwards seeing, oh, I've made a huge profit or I've lost 100,000 euros, you can simply, and this was what the exchange will do, the exchange will simply look at those daily profits and losses, and they will take those daily changes and they will adjust your account with the exchange. And it will look at those losses, and if your account is in the negative, at some point the exchange will ask you to pay additional margin, a security payment, eine Sicherheitsleistung, and a margin into your margin account. And if this happens, this is called a margin call. You are required to pay additional margins, additional cash into your margin account to make sure that in the end you cannot default on your future contract. What happens, and this is called marking to market, you're marking your account to market prices. What happens if you are not able to pay up the margin call? Yesterday I gave this example, you probably too don't remember this. Does anyone know the movie Trading Places with Dan Aykroyd and Eddie Murphy? Probably don't even know Eddie Murphy, and that's a shame. It's a movie in which 2 people switch places. One millionaire trader becomes a homeless person, and Eddie Murphy is the homeless person, and he becomes a trader, makes millions. And it's all due to a bet of 2 old exchange traders and the owners of a large trading company who make a bet of $1 that they are able to do the switch, that they can transform a homeless into a millionaire and a millionaire into a homeless. And later on, those 2, Dan Aykroyd and Eddie Murphy, they team up and they force those 2 guys into bankruptcy. And in the end, because they've bet on futures contracts, with the underlying being frozen orange juice. They have the wrong information. They are betting on, I think, a decrease. They have a huge short position, and then suddenly, at the end of the day, after they've realized that they have a huge short position and they're not able to sell it, suddenly the bell rings, trading is suspended, and then the officials of the exchange come to those 2 gentlemen, margin call. You have an open position of $180 million or $200 million, and those 2 characters say, "You don't, well, no, we don't have 200 million in cash." And then the exchange officials simply say, "Well, that's no problem. Let's acquire all assets of this company, file for bankruptcy, and offer those seats on the exchange to the bidders, and they are expelled from the exchange." This is a requirement, obviously, for an exchange to work, that the exchange makes sure that all traders are sufficiently liquid. And if they have short positions, and if they are not able to fulfill their margin requirements, they will be expelled from trading. And the exchange will make sure to acquire its funds. These are margin requirements and margin payments. This is one difference to a forward contract. Again, on the margin account at maturity, we'll see that the profit or the loss on this future contract is the spot price minus the initial future price at which we have bought the contract. And again, we see forward and future are virtually the same, with the exception that you have some slight details that are different due to the fact that futures are exchanged and traded on an exchange. You have a margin account, meaning that usually with interest rates being larger than 0, you would expect those payments and this cash on your margin account to be interest bearing. right now with zero interest rates. We can neglect this, and this is why we will see slight differences between forward and future contracts. Because in a future contract, you have a margin account. Those payments on your margin account, they will bear interest. In your forward contract, without margin payments, you simply have to wait until maturity and then you will get a huge payment, but no interest, of course. Okay. So, in the end, you will get the sum of all those differences in future prices times interest. This will appreciate with interest. And one difference, with a future contract, you can always settle it. You can always close your position because you can always sell the future again at the exchange. And this is why you don't have to wait until maturity, but you can prematurely sell it at a different point in time. So you have, if you sell it, you get this profit or loss, which is simply the difference between the future price at which you have bought and the future price that is offered right now for the remaining maturity. Okay. But again, the profit or loss position here is linear. With every euro the spot price increases, your future contract will appreciate or lose 1 euro. Okay. Then you have additional interest effects. This is not very interesting. This is simply if you want to settle it before maturity, you will not get as many interest and not much interest as before. Now, pricing. We only need this here. It makes sense not to look at each and every discount factor, but simply to capsule it in one variable R, that is the accumulated interest rate over all of those interest payments that are due on all those future payments. And then it's quite simple to come up with a price. One would argue that in a forward or future contract, pricing is very difficult. Why? Because if we buy 1 ton of steel in advance, 1 year, we have no clue what the price of steel will look like in 1 year. So one could argue that pricing is quite difficult. Actually, it's not. We simply have to compare these two strategies. First strategy is buy the underlying via a future and settle it in T, capital T. So your profit or loss is spot price minus the future price or forward price. Second strategy is buy the underlying with a loan, settle it at maturity, and repay the loan. And you see that this is just the difference of the spot price at maturity minus the amount of money we need today times 1 plus this accumulated interest rate, or this average interest rate. Both are identical at maturity, so both should have the same price in an arbitrage-free market. So we are not allowing what we call a cash and carry arbitrage. Very simple idea. So we can set this equal to this. If we do this on the next slide, and if we rearrange it, we'll get this. The so-called cost of carry price of the future or forward. The cost of carry price of the future is just what? The current spot price times 1 plus n. And the interest rate is now the accumulated interest rate or the average interest rate, but it's simply an appreciated spot price. So you don't need a Black-Scholes formula. You don't need any difficult mathematical models here to come up with a price for the future. It's simply take the spot price times 1 plus r. And right now, with zero interest rate, one would assume that it's almost close to each other. I actually haven't looked at this. I would assume that the change in interest rate should have a lasting effect on future prices. But this is quite simple. This is cost of carry price. Okay. If we rearrange it in a little different way, you can see that the basis is given by the cost of carry. You can, of course, use other interest rates. more sophisticated interest rate models and term structure models. In this case, I simply assume more or less an average interest rate. You can use a continuous or a linear approximation to those interest rates. And then you will see kt times 1 plus r over the remaining period, kt times a continuous interest rate, but it's always the same. Spot price times interest rate. Yeah, times, I appreciate the question. Now, let's look at some details here. The variance or the standard deviation of the future price is given, if we take the cost of carry price here, it's given by 1 plus r taken to the capital T minus tth power times the standard deviation of the spot price. Meaning that the volatility of the future price will decrease or increase to the volatility of the spot price simply due to the convergence of the future price to the spot price. So in the end, you will see volatility that is close to the volatility of the spot price, which is a simple result and simple effect due to the idea that the future price will become the spot price simply if we reduce the maturity and length of the contract. Next, let's look at the correlation between the future and the spot price. No big surprise here, the correlation is 1. Which is obvious from the fact that if the spot price increased by €1, the future price will increase by €1. Never mind. So we have a correlation of 1, and this shows you that this is a perfect hedging instrument. Go long in the underlying, go short with the future, and we'll have perfect negative correlation. Underlying goes up €1, future hedging instrument will go down €1, and they will cancel each other out. So you will have no variation. So at least theoretically, there is a perfect linear correlation between the future and the spot price. And in reality, unfortunately, this is not the case. In reality, the correlation will be less than 1. And this is what we call a basis risk. So if spot and future price are not perfectly, positively, linearly correlated, this is what we call a basis risk. And we can now distinguish two things. The theoretical basis, which should, in theory, be given by the cost of carry price, and an empirical basis, which is called the value basis. It's the same as with option pricing. You can observe a theoretical volatility, which is called the implied volatility, and the empirical volatility. And these two don't have to match. And this is basis risk. So every time you can see that the future will not be perfectly correlated with the spot price, you have what we call basis risk. And this is shown here. You will have a theoretical and an empirical future price. Those two will not necessarily match. And in the end, both, of course, will be at maturity, will be equal to the spot price. Okay. And this is basis risk. Here, you can also include dividend payments, which is no big surprise in the end that if you include dividend payments, the cost of carry price is the previous cost of carry price minus the dividends. If in between you get dividend payments, this will reduce the cost of carry price. Yeah? And this is given here. Of course, you need the terminal value. You need to include interest rate effects, but assuming interest rates are 0, this would simply be the dividend payments. Okay. I think I now have to make myself ready to go to our administration. Do you have any questions concerning forwards, futures, and plain vanilla options? Okay. Well, if you don't have any questions, make sure you look at the cost of carry price. This has been in one of the previous exams to show these two strategies to come up with the cost of carry price of the future. I think this is quite simple to remember. future price should equal spot price times 1 plus 1. But it's quite interesting to see those different strategies and the very simple way how we can prove this. And it's different to option pricing. We'll see that we need much more theoretical work to come up with an option price. Okay, so if you don't have any questions, thank you for your attention and see you next week.